You need to stop using AI agent frameworks. LangChain, LangGraph, Semantic Kernel, CrewAI. Don't get me wrong, these are great frameworks. But if you start your AI journey using them, you won't have basic fundamental understanding of how AI agents work. So you don't learn React before learning JavaScript, or you don't learn Flask before learning Python. You get the idea. So what we'll do in this video is build AI agents using pure Python and OpenAI APIs. We will cover different architectures like sequential, parallelization, and others. Everyone is fighting over what the best AI framework is. We're not even going to play this game. But before we start, let's do a quick recap of what AI agents are. I'm going to start from the basics and build up from there. So if you're familiar with a lot of these concepts, feel free to skip to the relevant sections. I know it drives me crazy when someone is talking about something so obvious that I'm familiar with, and I'm just like, move on. So I get it. That's why I have chapters. But I think this will be a relevant section even for those who are experienced, because in the overall industry, we can't even agree on what the definition of an AI agent is. Every company has its own definition. So at Microsoft, we define AI agents as systems that we can delegate tasks to. Other companies define agents as fully autonomous systems, so we can't even agree on that. But in a nutshell, it is an application that uses a large language model as its decision-making engine to decide what actions to take. If you have a weather API in your code and the user asks a question, what's the weather like in Paris? The LLM will understand that question and it will know that it has access to a weather API function, which it will instruct the application to call and retrieve that information before surfacing back to the user. That's the most basic form of an AI agent. The more advanced version of an AI agent is when a large language model dynamically alters its decision-making process. Let me explain what I mean. We've all used the deep researcher feature in many of the popular chatbots. This is an example of an advanced AI agent because it searches the web, it reasons on the results that it got from the web, and it will only stop once it deems that the results are satisfiable. Okay? So this is not something that the human would define in a step-by-step workflow. The agent will only finish its task once it gets to the relevant quality. So Replit AI agent is actually another example of an application where you can use natural language to build end-to-end applications. So you just type what application you want to be built, and the agent does its whole thing autonomously, and only when it finishes these tasks, it gets you back the results. Now, of course, as humans, we most of the time have to define what the maximum number of iterations are because we don't just want them to do their own thing and just run into rabbit holes. Now that we understand what AI agents are, we still can't agree on a definition, but let's use OpenAI APIs and pure Python to build some of these things. And the first is just a basic chatbot. So this is using a chat completion API. We still didn't get to agent yet. So what we do is we create an OpenAI client so we can connect to OpenAI APIs using the key that we have on a .env file. We send the request to OpenAI asking their AI model, GPT-5, to generate a response to this message. So it's called completion because you provide your list of messages and the AI completes the list of messages by predicting what should come next. This is how LLMs work, essentially. And as you can see, even GPT-5 cannot agree on an AI agent definition. Now, in this example, we received unstructured text from the model. Okay, so if we're building a very simple chat application, we could just simply display this response directly to users and just call it a day. But in real-world application, we often need to use this response from the AI to make decisions in our applications, like, oh, based on this response, I want to do XYZ in my application. So we might want to extract specific data points from the response, okay? For example, imagine if we're building an expense tracker, and instead of getting back an unstructured response saying your lunch costed $12.5 at McDonald's on 15th of January. That's an example of an unstructured response. Instead of getting that, we get the AI to return to us structured data or semi-structured data in a JSON format as an example, where we would have amount, merchant, date, etc. And that would make it easy for our application to use that structured data to make decisions downstream. Working with output that is structured, that everything in our application agrees on and speaks that language makes it very simple. And you might be thinking, I get it. Can't I just ask the model via the system prompt to return back an answer with a structured format? And technically, you're not wrong. But the problem is that even if you ask the AI model to return the output in some kind of a structure, large language models are non-deterministic. So you can't always depend on an AI model to give you back a specified response. And this is where structured outputs come into play. Very important concepts in AI agents. This will always ensure that the AI model returns back a response that adheres to a structure that we define. To do that practically, we use the Pydantic library, which allows us to define data models and specify what each data type should be. So in this case, we have a calendar event class that is inheriting from the base model class from the Pydantic library. And this is defining what the structure of the output that we want, which is going to be in the form of name, date, and participants. And of course, when we send that request to the AI model, we specify that we want the response format to adhere to the calendar event class. So now the response that we should expect from the AI model shouldn't be randomly unstructured, but it should adhere to the structure that we defined, which is name, date, and participants. So what we're saying in the system prompt, extract the event information, and the user question is going to be Alice and Bob are going to a science fair on Friday. So we would expect it to capture the name of the event, the date of the event, and the participants of the event. And if you run that, you can notice we got a structured output that adheres to the structure that we defined. Now let's get into tools. Let's build from our basic chatbot and let's give our AI application access to tools. So what do we mean by tools? They are basically functions or actions that our large language model has access to. So by itself, our large language model can only generate a response. But what if you wanted to search the web, search a database, call an API, and do all of that before returning back a response to the user? The web search in ChatGPT is actually a perfect example of that. And in fact, here is a code example where this is provided out of the box in the OpenAI documentation. This is nice because previously we had to define a separate web search function and provide it to the large language model. Of course, instead of using these out-of-the-box tools, you can give your large language model access to custom written functions in your code that call an API, a database, or do anything. This is known as function calling. So function calling is the large language model's ability to tell your application, I need access to this function when the user asks a specific question. For example, if the user asks what's the weather like in Paris today, the large language model won't be able to give that answer due to the cutoff date. So what it does, it knows it has access to a weather API function in the application, and it instructs the application to make that call to the function to get the weather details before surfacing that response back to the user. Now, it's a bit more nuanced than that, so let's get into an example. As you can see, we defined the actual weather API function. So this is using a public API. We're passing a latitude and longitude as arguments. And then we follow the same exact steps as before. So we define what the client is. And then we define the tools that our AI model will have access to. It is an array because we can have multiple tools. And as you can see, the type of this specific tool is a function, and we give it a specific name that matches the actual weather API function that we have. We also need to describe this tool as best as possible because the large language model will use that description to know that it has access to this specific tool. So once you have multiple tools in your application, you need to have very accurate descriptions, so the large language model has an easy time knowing which function to call. And of course, we have to specify that this specific function would accept latitude and longitude as arguments. So then we scroll down and then we make an API call to OpenAI specifying the model and the tools along with the question. So in this case, we won't get the final response from the model. We will get a response back specifying to call the function with the relevant arguments. There is no magic here. All the model is doing is it knows that this is a weather question. It knows it has access to weather tools, specifically the weather tool function, and what the argument it expects. So it gives back a response saying model wants to call getWeather function with these specific arguments. So I'll show you how that would look like in a bit, but there's no magic. So we define the call function. In this case, we're going to get back to it. This is where we actually execute the function call. So we will loop through the collection of tools just in case we have more than one tool. We extract the name and the arguments from the response or the initial response that we get back from the model. And then we print the model wants to call this specific function with these specific arguments. Then we append all of that into the messages history, which we'll use in a bit. And then we execute the call function. We pass in the name of the function and the argument. If the name of the function is getWeather, we will call the getWeather function with these arguments, and the getWeather function is defined on the top. Once we execute the function, we append all of that, so the result from the function, into the messages history. And we finally get back the final response from the model by providing the history of the messages, which again contains the weather API response and the user question, and of course the tools that the agent has access to. And we finally get back the final response. Let's try to run this. As you can see, we have the initial response and the final response. The initial response contains instructions on what function to call. So this is the name of the function, and these are the arguments that will be passed to the function. So the latitude and the longitude are what the large language model knows, and it will pass these arguments to the application so that it can pass it to the getWeather function. And this is the result from the weather API. And we synthesize all of that into final response, which is the current temperature in Paris is XYZ. Very simple to implement. Now we get into retrieving data. So how do we implement RAG from first principles? In this code example, we create a vector store on OpenAI servers. And what we do is once we create that vector store, we upload a local file that we have which contains customer policies, and OpenAI will automatically break that file into chunks, convert it into vectors using an embedding model, and store them into this vector data store. And then we would have the capability to search for the data in that store. So in this case, the user query is what is the return policy. We use that query to search for results in that vector database. Now we can wrap up here if all we want is just to get back a response from the vector database. But in RAG, we typically want to synthesize that data. So we want to use the large language model to take that retrieved document from the database and synthesize it somehow. Maybe provide a more concise summary. Maybe return it using specific domain terms. Whatever that is, we want to use the large language model to synthesize that response. So we're not going to stop here. That is exactly how we will implement that logic. So we will format the results that we get from the vector database, and then we call the OpenAI model with this specific system prompt, which is saying produce a concise answer to the query based on the provided sources. So this is how we are synthesizing this response. And of course, in the user prompt, we are providing the formatted results that we got from the vector data store and the actual user question. Pretty simple to implement. Let's try to run this. And as you can see, we managed to retrieve the return policy from our local document that we stored in the vector database, and we managed to put that into a concise answer that was provided by the language model. Now, in this example, I want to implement RAG as a tool. So what we did in the previous example was what we call traditional RAG. So we used to implement that before agents and tools were really a thing. But a vector search can just be a tool in your agent. And the benefit of using a vector search as a tool for RAG is that this tool call only happens when it's needed and not with every user question as we had previously. Okay. And of course, you can also combine RAG with other tools as well. So implementing RAG as a tool is a lot more powerful. So in this case, all we need to define is a tool that is able to search for data in the vector data store. So let's go through an example in this case. We set up the knowledge base. We upload the local document that we have, which is customer policies. And then we define the search function. This is what will be used as a tool for our agent. Of course, we specify the vector store in this case. And then this is where we define the tools. So in this case, it is also a function. The name of the function is search underscore knowledge underscore base, which we defined here. All it does is that it searches for the relevant documents based on the user query. And we get back the formatted results. And of course, we specify what the arguments that we need to pass to this function. In this case, this is just a string that contains the user question. So we scroll down, and this is where we test different types of questions. First of all, let me go through the system prompt that we outlined here. So what we're saying in this system prompt is that you are a helpful customer service assistant, blah, blah, blah. But more importantly, we're specifying when users ask about company policies, procedures, or specific company information, use the search knowledge base tool to find that information. And this is very important because this is what's going to allow the model to dynamically use this tool. We don't want this model to always perform a vector search for every user question. We only want to do it in specific scenarios, which we are specifying in this system prompt. So we pass the list of message history, we pass the list of tools, and then we check if the model wants to use tools, because remember, we are going to get back the initial response. Once we get back that initial response, we append that to the message history. We execute the tool calls. In this case, we only have one tool call. So we're going to extract the name and the arguments that we got from the initial response. And of course, we would call the function with the name of the function and the arguments that we need to pass into the function. In this case, it's just a user question. And then we finally get the final response back. Pretty simple to implement. And what I've done here is I've actually tested this with multiple questions. So I've tested this with questions where the application has to leverage the search tool. And I've tested this with questions where the applications should only use general knowledge, not the tool. So in this case, this is a math question. I would not expect the application to use RAG for that. So let's actually test that. You can see the user asks, what is your return policy? The model uses RAG in this example, but when the user asks a generic math question, the model answers from general knowledge. That is brilliant.
Right, so what we did so far is just build single agents, which is not very exciting. Most of the time, we end up building multi-agentic systems. And to do that, there are many different architectures that we will go through in this module. The most basic architecture is called prompt chaining. So what we do with prompt chaining is that we call the first agent, that gives an output, which is then used as an input to the second agent, and so on and so forth. And this is great for tasks that can easily be broken into subtasks, like generating a marketing copy and then translating into a different language as an example, or even using this as part of a data processing pipeline as an example. The second type of architecture is known as parallelization. So this is running parallel agents together. So that could be a series of different agents doing research or analyzing multiple customer reviews at the same time. Very, very powerful. The third type of architecture is called routing architecture. And this is when you have a router that classifies an input and directs it to a specialized agent. So this prevents optimizing for one kind of input, which can actually hurt the performance of other inputs. So examples of that is directing different types of customer service queries, as an example, to the relevant agent. Or the most common one that I see is actually routing easy or common questions to smaller models. So routing is very powerful, very heavily implemented as well. The last architecture is called Orchestrator. With an orchestrator, you have an orchestrator LLM, which breaks down the tasks and then delegates them to other specialized LLMs. And then once all of that happens, you synthesize all of that as part of one answer. So this is very powerful for complex tasks where you really can't predict the subtasks that are needed. So the subtasks themselves aren't predefined, but they're actually determined by the orchestrator based on the specific input. And deep research is actually a perfect example. So that involves essentially gathering and analyzing information from multiple sources for possible relevant informations. And we typically need an orchestrator that decides what specific topics we have to research, because not only one topic. You might be trying to research one topic, but that is typically broken down into subtopics, and that is what the orchestrator actually decides. This is how many of the deep research agents actually work behind the scenes. Let's actually go through code examples, starting with a prompt chaining code example. This is going to follow a lot of the principles that we've already discussed in previous examples, so I'm not going to spend too much time here. This is the beauty of starting from first principles, because really, a lot of the things that we will go through in this example and the consequent examples are things that you already know if you're paying attention in this video, which you hopefully are. So what we're going to do in this prompt chaining example is we're going to do a simple content moderation. So we have a specific piece of content and we want it to pass through a series of agents that are going to analyze this content for moderation. So we're going to have the initial agent, which does the quick analysis of the content, and we want to have the agent return us back a response in a structured format, as you can see here. So that is why we are defining all of these classes. Then we have a second agent that does a deep analysis of potentially problematic content. So once we do an initial quick analysis of the content, we have a confidence score, and then we have a risk level. And based on these, we're going to use that information to decide whether to pass to the next chain or not. Okay. So if we see that the risk level is high, we would go to the next agent, which does a more deepened analysis. And then finally, we go to the moderation decision agent, which makes the final decision based on all of that. So this is actually what gets returned to the user or whatever moderation system we are building. And all of these are using structured outputs, which we've already explained. So these are the actual functions for each agent, essentially. So this is the initial analysis agent. This is the system prompt for that. And this is when we would call the model with that specific system prompt and the content that we will supply. In this case, it's going to be hard-coded. Of course, the response format has to match what we defined above as well. This is the detailed content review, which is the second agent. We follow the same steps. And this is the final agent that we defined, again, with a specific system prompt as well, adhering to a specific structured output format. And that is the main chain function or logic for the prompt chaining agents. So what happens in this case is we are going through a set of gated validations. So what we're going to do first is we're going to run the initial analysis. So we're going to call the analyze content function, passing in the content. We're going to check the confidence score. If it's low confidence, then we might want a human to review that, or maybe the try. Once we pass that stage, then we go to gate 2. We check if the risk level is safe. And if it's marked as safe, we don't have to go through the entire chain. So we can save some money. Once that happens, we simply return moderation decision, which is the final decision, and that's going to be approved with an explanation as well. Now we go through the next chain. This is when we would have to run a detailed review, passing in the content and the initial analysis. We go through certain logic. So if the severity score is less than 3 and it's warned, then this is a low severity issues. We convert it to approval with a note. We go through similar pieces of logic. So in this case, if the severity score is greater than or equal to 9, then this is a very severe score, which means that we need probably human moderators. In a nutshell, we have a series of if-else statements and business logic to go through the set of chains that we have, which are gated. So that is basically an example usage with different types of content. So I am testing this with a content that is deemed safe as an example. Then I'm going to test this with other contents that are spam in this example. And I should expect different results from this prompt chaining agents. So I'll try to test this. So here's an example of moderating safe content. So in this case, the decision is approved with an explanation, pretty simple. And this is an example of moderating spam content, which is a bit more rigorous because it passes through the entire chain. So in this case, the decision is removed. And here's an explanation for that, and so on and so forth with other types of content. Make sure to play around with this. Again, the link is in the GitHub description. The more you play around with this code, the better you can understand it. But hopefully I explained this a bit more simple. The next example that we're going to go through is the parallelization example. And this is not going to be any different from the sequential example that we went through. The only small change that we will have is instead of calling the OpenAI's APIs synchronously, we're going to call them asynchronously. So for those who don't know, synchronous AI calls basically block the thread until we get back a response from the API. So this is great if we try to run things in sequence, okay? So the thread is blocked until we get back a response, and we move on to the next thread, okay? With asynchronous API calls, you make the API calls, but the thread in the code or in the runtime is not blocked, okay? So you can make multiple asynchronous code or calls that are non-blocking. That's exactly what we're going to do with asynchronous API calls in this case. And I'm going to use an async OpenAI library, which we'll use to define our client. But we're going to follow the same exact logic that we had previously. The other minor change is we're going to specify maximum concurrent calls, because whenever you're making parallel calls to the AI model, you can be subject to rate limiting, okay? Since I'm using, in this case, one OpenAI account, and I'm making multiple calls in parallel, I might hit the rate limit pretty soon. Okay, so I'm just specifying the maximum number of concurrent calls in this case. What we're going to do in this example is we are trying to analyze different product reviews in parallel. Okay, so we have a sentiment analysis agent, we have a feature extraction agent, and we have a review summary agent. And we want all of these to run in parallel. Very simple, exactly the same as the sequential example that I provided. The only difference is that we are making asynchronous API calls with this await queue, but it's following pretty much the same exact logic and workflow. So this is the main parallel processing function. So what we do is we call all of these three different functions with the review as an argument, all in parallel using this async IO flyback. Once all of that happens, we combine all of these results into a single dictionary. That is pretty much it. And that is basically another function to analyze multiple reviews. So you can have multiple agents running in parallel to analyze a single review, or you can have multiple agents in parallel analyzing multiple reviews. These are just two different examples, okay? And this is when we test the parallel processing. So we have sample reviews. All of these are hard-coded. Let's go through an example of that. So you can see the review 1 results, the review 2 results, and the review 3 results. All of these are running in parallel. Beautiful. Next, we're going to go through a routing example. So what's going to happen in this case is we are going to try to analyze a customer support question, okay? So we're going to have an initial router agent that determines what type of support request that is. It's going to classify this, and based on that classification, it's going to route it to a specialized agent. So this could be an agent that is specialized for technical support issues, an agent for billing and payment issues, an agent for general inquiry, complaint details, support response. We've got many, many, many different agents. So we've got one final agent in this case, which actually sends back the response to the customer, okay? Multiple agents in this case. As before, we define a function for each agent. So in this case, this function is going to get the customer message. We write the relevant system prompt to classify this customer message, and of course use structured output. In this case, we send that to the model, we get back a response, we define the same function or different functions for the different agents. We go on and on and on and on. Yeah, there's too many different agents. I'm not going to spend too much time here because I think hopefully at this point everyone should be familiar with what's going on. So once we define the structured outputs and once we define the functions for all of these agents to make the actual API calls, we define the main orchestration function, okay, or the main business logic. So what we're going to do here is that we're going to call the root support request function, which we defined above, passing in the customer message, and then we should get back a root result based on the structured output that we defined. Then we go through a gating system that we went through before, and if the request type is technical, we simply route it to the technical agent. If it's billing, we route it to the billing agent, and so on and so forth. That is really pretty much it.
All we're doing is just calling the specific function depending on the specialized agents, making sure we pass in the relevant arguments. That is pretty much it. And this is when we test the routing systems with different types of customer messages. Let's run this. So you can see this is the question that we got from this fictional customer, and that is the response that we got back from the model with the troubleshooting steps. So what this did is that it actually understood from the question that it has to route it to the technical agent. Okay, so very neat example of a routing architecture. Again, I've seen this implemented a lot of times to determine which model to call based on the question. And a lot of times you end up calling smaller models for very simple questions and maybe more complex and reasoning models for more complex questions. And last but not least, let's go through an orchestration architecture coding example. This is going to be a bit more complex, but not too much, to be fair. We're still covering the same exact principles that we went through previously. Guys, make sure that you access the GitHub link that I have on the description and play around with this code, because I could try my best to explain this code as simple as I can, but you're not going to be able to understand it, and you're not going to be able to understand basic principles of AI agents until you play around with that code. Play around with it, get some errors, debug it, break things. That's how you learn, okay? With that out of the way, let's go through this orchestration example. So what I'm going to do differently here is I'm not going to go through these different classes where I specify the structured output because I think this is going to confuse us at the moment. Let's go through the functions that we've defined for each of our agent, okay? So what this orchestration agent will do is that it is going to receive a research question, and then it's going to determine, based on that research question, which specialized group of agents to call. So as you can see, as part of the system prompt, we tell it, create a comprehensive research plan with specific tasks that specialist researchers can execute. So once we do that, we define the specialist LLMs that would execute these specific tasks. Notice we're not hard coding the tasks in that system prompt because we will get that research task from the orchestrator along with the context, okay? So you can see this is a bit more generic. Nothing is hard coded. So each specialist focuses on one aspect of the research, like competitor analysis or market sizing, etc., etc. So in this case, we are logging specialist execution task based on task type that was determined by the orchestrator. All of that you see here is not hard-coded. This is going to be parsed by this API. And then finally, we have a synthesizer agent that simply combines all of these results into a final report. That is pretty much it. I'm not going to go through that in more detail, but that is the main orchestrator system. So I've defined different functions or methods inside of this market research orchestrator class, just a better way to organize the code. So we store the task results in an empty array initially, and then as they're being completed, we simply append them to this empty array. So the first thing we do is we define the main orchestration function that manages the entire research process. So this will break down the request into manageable tasks. It will have specialists complete each task independently, which we're going to see in a bit, and then synthesize all of that into one comprehensive report. So this is when we would call the function create research plan, which is the orchestrator. And then we create the context, which is understanding the bigger picture of what the question is actually about and the research objective and all of that stuff. And then we would call the specialists agents. Okay, so for each task that orchestrator comes with, we would execute a specialized agent passing in the task and the context. Once all of that is done, we write the final report, passing in the research plan and the task results that we got from these specialized agents. That is pretty much it. It's a bit more complicated, but again, it's following the same exact principles that we went through. So this is where we test the usage. In this case, we're going to do deep research on an AI-powered personal finance app. Let's try to run this and see if we get a good result. Now, notice this is going to take a lot longer than the previous examples. That's what we would expect from a rigorous deep research system. And by the way, a lot of these principles are actually what is implemented behind the scenes on a lot of the deep researcher tools that you use. Now, of course, they are a bit more rigorous, but they're following the same exact principles. If you want another video from me that goes through an entire example of how we would build a deep research agent from scratch, let me know in the comments. I'm happy to do that. But this is a more simplistic example. There's a lot that actually goes on behind the scenes to build a deep researcher agent. It's a lot more complicated than we would expect. I know these are tools that we use every day. We take them for granted, but there's a lot of work that goes into building these deep research agents. One, there's lots of agents. Two, there's lots of context management that you need to make with different agents that might have different conflicting information. You need to be able to manage parallel execution. There's a lot to think about. System prompts is just a whole different beast as well for each of these agents. So there's generally a lot of things to think about when you're building these deep research agents. So enough of my rant. I was just trying to buy time to wait for this to finalize, but it still didn't finalize. So let's give it some time. And finally, market research process completed successfully. Look at that. That is a pretty comprehensive research report. Not bad for something that we've implemented without using any kind of framework. Love that. Again, link is in the description. Make sure to play around with it. This is the only way you can understand all of these code examples. And that's a wrap. You might say, why did we have to bother with all of that? Because I think it's important to start from the ground up and build from there. A lot of these patterns can be achieved with just a few lines of code because they are completely abstracted by these frameworks, which is fine, But once they break, you would have no clue what's happening behind the scenes. But now, having gone through all of these examples without using any framework, you can at least guess and build a bit of intuition on what happens behind the scenes just in case these frameworks break. Because in production, you're going to use a lot of these frameworks like LangGraph. But when they break, it's very hard to understand what's happening behind the scenes. But hopefully with these examples, you would have built a bit of intuition to hopefully help you debug some of the future issues that you might run into. And hopefully that will make your lives a lot easier. So with that said, if you enjoyed this video, check out my full generative AI course on YouTube, which is a 4-hour course that goes through everything you need to know about generative AI, building AI applications, agents, MCP, etc., all completely for free on my channel. And with that said, thank you for your time.